Good morning, everyone. In today's lecture, we'll talk about the electric charges and the atomic structure. Benjamin Franklin was an American scientist who hypothesized that only two charges exist, positive and negative charges. He also proposed this famous kite experiment to demonstrate that lightning was an electrical phenomenon, where he hanged a key in a insulating string and put it up in the sky during a thunderstorm. So what do we know today about the charges? We know that there are three particles do exist in the atom. Those particles are electrons, protons, and neutrons. Protons and neutrons, they do exist in the nucleus of the atom. However, the electrons are floating around. So if we look at the structure of this atom, this is the nucleus here inside that has the protons and the neutrons, while the electrons, as you can see, are floating around. Now, neutrons are electrically neutral. However, protons, they have a positive charge that is the same magnitude of the electron, which is E. So E here is the magnitude of the charge, either an electron or a proton. However, protons and electrons, although they have the same charges magnitude-wise, their mass are completely different. Protons mass is 1.673 to the power minus 27 kilograms. Electrons is 9.109 10 to the power minus 31 kilograms, which means a proton is almost 1,800 times heavier than the electron. What is the unit of this charge? The unit of the charge is Coulomb, and this is the international system of units. So the unit for the charge is Coulomb. So we have protons that are positive charges. We have electrons that are negative charges, and neutrons are electrically neutral. So if we look at this atom here, atoms, when the number of the electrons equals to the number of the protons, the atom is electrically neutral because the number of the electrons equals to the number of the protons. However, when an atom loses an electron, the number of the protons becomes greater than the number of the electrons, and in this case becomes a positive ion. However, if this atom gains an electron, then the number of the electrons would be greater than the number of the protons, and in this case, I will be having a negative ion. Now, the same thing here for any object that gains electrons becomes electrically negative. If it loses electrons, becomes electrically positive. Same things as we saw here applies on the atoms. Atoms that gain electrons becomes electrically negative, and that's why we call it negative ion. Atoms that loses electrons becomes electrically positive, and that's why it becomes a positive ion. So if we have two objects that are charged with the same charges, in other words, if I have two objects that are electrically positive or electrically negative, in this case we will call them having the same type of the charges. In this case, those two objects will repel each other. However, if the charges are opposite, so one of them is electrically positive and the other one is electrically negative, then those two objects, they tend to attract each other. Now let's look at this simulation that I included the link for it here for you to try it. If we have this balloon, as you can see, has negative charges that are equal to positive charges, so it's electrically neutral. However, if I bring this balloon, as you can see, wherever I put the balloon stays in its place. If I bring this balloon and rub it against this wall, in this case, the balloon will gain electrons and the wall here coat will lose those electrons. So this balloon will become electrically negative and the coat here electrically positive. So as you can see here, if I let the balloon go, we'll talk about the wall later on, but if I let the balloon go here, it will be attracted toward the coat, as you can see here. However, if I bring now this balloon that is electrically negative and put it against the wall, it will also stick. Why is it going to stick here? Because the balloon is electrically negative and the charges inside this wall will not jump to the balloon. It will move freely in the wall. As you can see here, the negative charges, the electrons moved away. When the electron moved away, now the positive here charges becomes attracted to the negative charges in the balloon, and then the balloon will stick to the wall. So by that balloon moving away or repelling the electrons in the wall, then an attractive force will induce now between the balloon and the wall. If you notice anywhere, if I rub this against this coat, then I can collect more electrons. Notice what's going to happen now here to the charges in the wall. Now I have more negative charges here, more electrons on the balloon. That's why those negative charges repelled the electrons in the wall, and now I have here the positive of the wall attracting the negative on the balloon, and that's why the balloon is sticking to the wall. If I move this one a bit far, then the balloon will be attracted to the wall. Okay, so any two charges that are from the same type will result into a repulsive force, and the opposite charges will result into an attractive force. They will attract each other. So in this course, we will talk about this fundamental force that is made of electromagnetic force. As you can see in the previous slide, this electrostatic force was one of the special cases of the electromagnetic force. You have seen earlier in earlier physics courses one of the fundamental forces, which is the gravitational force. Here in this course, we will talk about this second fundamental force, which is the electromagnetic force. The remaining two forces uh, are not covered in this course, which are the strong and weak nuclear forces. So here we will focus on the electromagnetic force. So why electrostatic charges are important, and what are the popular applications that we use on a daily basis that involves the electrostatic charges. One of those applications are really your mobile phone. Your mobile phone, that touch screen, or the iPad, or any touch screen device, basically has it's a screen that is sensitive toward charges applied by your finger or by your stylus, the pen that you're using. And in this case, by disturbing the charges that already exist on that touch screen, will result into the your tablet or your mobile or your computers noticing a change in the charges at this location, and then sending a command to the processing system, such that this location has had a touch, and in this case, the computer or the iPad or the tablet or the mobile will execute any command that is related to this location on the touch screen. A second application that really has electrostatic charges utilized in is the laser printing, where in this case, in the laser printing, here we have this lamp, neutralizing the drum, and this drum that is rotating will then go into a wire that is spreading positive ions on this drum, and then the next step would be this laser beam that is uh, made of electrons that are shooted based on whatever shape or pattern you are printing, you're scanning into this printer. It would be transferred into those laser beams, and in this case, those letters or this pattern will be drawn on the drum, and then later on, when this drum continues rotating, those locations that were defined by this laser beam will be filled with a toner that is positively charged, will be attracted by those patterns that are now made of negatively charged pattern. Those pattern now will attract the toner, and then you will see that the shape or the pattern you are printing will be now filled with the toner, and then will continue rotating, and this shape now will start to be transferred into the paper, and then this paper will go into a heater section where that toner is being heated in the paper. And that's why when you print on a laser printer and you touch the paper, right, it comes out of the printer, you will feel that it is hot. It is hot. Why? Because it was cooked. This toner that was attracted and put on this paper is later on heated up, such that this toner will be permanently fixed on that paper. So so far we've seen how are those charges are distributed within the atom, in the nucleus and around the nucleus. Also, what is important to know that those charges are quantized in a way that we treat that charge of an electron, which is 1.602 to the power minus 19 coulomb that we have seen earlier, as our minimum charge. We cannot go smaller than a charge of electron. Put aside the quarks for the time being. Let's focus on the electron in this course as the minimum charge. So here, our minimum charge is the charge of the electron. We cannot go half an electron. So the charge of the electron of one single electron, for example, or protons, which is the E, the one that we have seen earlier, is our minimum charge. This is the smallest charge quantity. So when I say later on, I have this amount of a charge, this amount of charge has to be an integer number of this E. So this Q has to be an E at the end. The second, the second feature for those charges, that those charges are conserved, not only quantized, but they are also conserved, which means that those charges cannot be created or destroyed. They all go from one shape to another.